Okay, so good evening, everyone. I'm Calvin Joseph. I'm going to be conducting the week 7 problem solving and doubt clearing session. So, which is basically it is introducing you to Verilog and some examples are there. What are the various basic oh, 21 minutes. So, are you guys able to unmute?
Yeah, I am unmuted only already.
Okay, but Rajesh Sekhar was saying some issue of not able to unmute it. So, Rajesh Sekhar, could you tell?
Okay, maybe if when he want to talk, I guess unable, I guess, and
Yes,
it is
yes.
asking your permission to unmute his mic.
Oh, but that wasn't happening last minute. Okay, so you're not able to unmute then Rajesh Sekhar. Okay. So then so my screen is visible here.
Yes.
Continue. So today I'm discussing about Verilog, about how what is structural modeling in Verilog, how data flow modeling is handled. Okay. The behavioral modeling in Verilog. Also, then I'll be discussing a lot about the number systems and regarding fixed point implementation also. So how what is queue format, what are the various types of number representations, etc. And also I will be showing how counter-based DPWM also is Verilog code is written. Okay, we will try to understand that. So apart from that, from last week, do you guys have any query or any doubts?
Last week I did not attended.
Okay.
But if anything is there, I will ask later, but not right now.
Okay. Fine, fine. Okay. So we'll go into Verilog. So in Verilog, Achha. So now when we write Verilog code, at least the one way is restored, you will write the Verilog code in a module. Okay, the everything is visible and proper, right? So now module consists of a basic building block. So why do we write a module? So one set of code which pertains to one particular function, we will write in a module, and so that way it is in a modular structure which we can, whenever we need that set of code, we just have to call that module. Okay, so in that way we can specifically test each module, and then when we want to combine all these modules together, we can get a bigger. We can call those smaller modules in a bigger module, right? So this is how you define a module. So when you're writing Verilog, you have a module and its module name. So the name should be something which is not a keyword. Okay, the module name should not clash with the keyword, otherwise your compiler will create an error. Okay, and then we will have a list of output and input terminal list will be there, like which is the output, which is the input, and then what functions you want to write in the module, it will be present in the module. Okay. Then okay, so this is how there's a module is given over here, and the inputs are shown, and this is where the inputs are, and this is where the outputs are. So inside the module, we will write the code of what we will do with the inputs and what will be the output, etc. We will write inside that. Now, this is a module. Consider this is module is a full adder module which Sir is taught. So what Sir is doing in what is there is half adder modules are called inside this full adder module. So in the full adder module, I will be using half adder modules, and I will, how many half adder modules I will call, I will name each half adder module which I need a different name. So this is half adder 1, half adder 2, etc. That is means I am calling those half adder modules. Okay, but one thing we must be clear is we must not define one module into another module. So we will define a module and all the code regarding a module in itself in a separate place. And then when we require that module, we will just call that instance of that module. Okay. So, so here in this part, it is shown how we must, what we have done is we have written a module for full adder. FA stands for full adder. And in that module, they've written the code for a half adder. They've written the entire code. They've defined the half adder module, and they've written the code of the half adder module and ended that module. So this is not permissible. This is not allowed. Okay, so instead over here, what they've done is we have written a full adder module, and in the full adder module, we are calling each half adder module one by one. Okay. Okay.
Yeah.
Yes, yes.
No, I said yeah. That's it.
Okay. All right. So this is how what is present in the module we will see. So first of all, we have our module name. Okay, the name of the module. Then list of ports is like the input and the output. So we will write the list of the input and output which we want. And then we will write over here that, like, see, we will write like we want ADC data, DAC data, or we want the clock, etc. We will write over here that these are the ports. Now the port can be input or output. So then over here we will write input. And these are the ports which are the input, and output we will write the list. Okay. Similarly, some parameters which we require, like the gains of the PID controller, etc. that we will write. Then we will declare the wires or registers. So what is a wire? What is a register? I will tell in the later part. Then what are the data flow statements? Then how, if we require any lower level module, then how we call those lower level modules, etc. And other things regarding the task and function for which we have defined the module. So this is just like a basic structure. So in this structure, we will write our various codes, okay, of how it has to be executed. So this is the example of a half adder module which we have. So this is half adder. We are defining the half adder module, okay? And here we have the sum C, A, comma B. So A and B are the inputs, and S and C are the outputs. So we write over here input is A, comma B. So these are the signals which are coming input A and B, and we have defined in the module that A and B are my inputs. Then we have the outputs are sum and carry. Okay, we have given it a variable name S, comma C. All right. Then we know this XOR gate. XOR gate, we will do, you write the sum S is the XOR of A, comma B. So XOR is already present. The XOR function is already present in Verilog. So we don't need to write the XOR function. We are just using that XOR function. We are calling that XOR function. Okay, it is like a Verilog primitive, means it is already inbuilt in Verilog. We are using this inbuilt Verilog function of a XOR gate. Similarly, for carry, it is the AND operation of A and B. All right, so we are using two gates, gate 1 and gate 2, and we are defining our half adder module. So this is how we completed the module. And like this is the gate structure of how the internal gates are there, which is synthesized. This block is synthesized in Verilog in this form of these gates, and that will be used to get our output from the inputs. So any doubts still here?
No.
Right. So this model does not have, okay. Okay, so G1 is my gate 1. Okay, this is just the name gate 1. Now ports are my input and output. Okay, so as you would have seen in the last thing, we had written This is input A, comma B. All right. So they are separated by a comma, and then they have to be ended by a semicolon. Okay. So both input and output both have to be ended with a semicolon. Everything. Once you write a line of code, you have to end it with a semicolon. If you don't do it, then it will throw an error. Okay. So this is something which you must have it known to you. Like another simple thing is so sometimes, so one thing is module you start, you have to do end modules. Suppose you're using begin function somewhere. Then what you do, what I'd recommend is you write begin and you write end over there. And then you click enter and write create space. What happens is sometimes we have one begin over here. Then we don't write it. Then we start a begin over here. Then we write some end over here. And then we forget to write this end. Then what will happen? The compiler will throw an error. And then when the compiler throws an error, we don't know. We have to go through painfully step by step to find out where was the error. Okay, there are some, I don't know about other softwares, but in this Xilinx software, at least I did not find that it recommending the begin and end simultaneously. So probably in the other programming languages, if you see, like if you type begin, it will automatically write off end. Okay, it will automatically go, but here it will not do. You have to write. So I'd recommend whenever you're writing starting anything, you also write the end part and then you write the code over here. Okay. Don't just write begin and then do if A is less than B, something like that, write your code. And then you might forget to write end. So whenever you write a begin, you do write an end immediately. And then between the begin and end, then you write the functional code in between. And this is just a simple thing to get rid of errors, unnecessary errors, which might pop up. Okay. Yeah. So this input and output, how the list of ports, everything we have told. Now, how can we write this? All right. So if you see over here, this is my module of the full adder module. And this is my half adder module. So the half adder module is being called instantiated in the full adder module by this HA1. Okay, HA1 is the name of the object for the half adder. So we have defined half adder. The first argument is S, that is sum. C is carry, A is the input, and B is the data thing. All right. So this, if we have defined it like this, then when we call this function over here, we must call these arguments of the function in the same order. If we don't do this, what happens is if you write HA1 is S underscore 1, A carry underscore 1, B, then it will throw an error. Okay, it will give erroneous result or it will throw an error. So because it will not throw an error, it will give an erroneous result. So it will give A, it will give the output, C underscore 1 will be taking the input, and it will not work actually. So this is not acceptable. So if we are writing like this, then we must write in the same format. Yeah, okay, I'm sorry, I apologize. It will actually throw an error because the input is A comma B. And it will want it in that order only. All right. Now, okay, so this is how a full adder is made of two half adders. Okay. Now another thing is we can either call them by the dot S. So in this case, let us say we have half adder 1. We call dot S of S underscore 1. Then we can call dot A of A. Then dot B of B. Then dot C of C underscore 1. Even if we do that, it will not give an error. It will not generate a wrong result because in this we are specifying through the Verilog compiler, etc., that my dot S variable, this dot S variable will take S underscore 1. So S which is inside in this thing, what is my S will be this S underscore 1. Okay. What is my C inside this module will be my C underscore 1. What is my A inside this module will come from here. What is my B will come from here. Okay. So that it will know. It will define from the dot. So the advantage in this method is we do not need to write it in the same order. Like this is in this order. we do not need to write these arguments when we are calling it inside another module in the same order. We just call it by the dot of s of that, and then we give whatever variable we want to pass. Okay, so that is the advantage of using this method. So is there any doubt in this regard?
No, it's clear.
Okay. And Banerjee, you're having any issue? Okay. Okay, Sanjay. So in the previous method over here, okay. Yeah. So Banerjee, you're also not able to unmute. Okay, fine. So in the previous method, what was happening was we in this full adder module, we are calling this half adder. Okay, and these variables which we are passing to this half adder module, we have to define it in this same order. So suppose over here we wrote half adder 1 is s underscore 1 a comma b comma c underscore 1. Then what will happen? It will throw an error. It will give the wrong result. Because what it will do to variable b and variable c underscore 1, it will treat it inside this code. This will be assigned to a and this will be assigned to b. Okay, by and this a will be assigned to c and this will be assigned to s. So if we do that, our code will give us the wrong output. It will function wrong. It will give us the wrong output. Okay. So if we are calling this half adder in this way, then we should remember the order in which we have defined it. But it might not always be possible for us to remember the order. So what we can do instead, we can call half adder 1 is dot s of s underscore 1. Then dot a of a. Okay. Dot b of b. Dot c of c underscore 1. If we do that, it will work properly. It will work fine. So that's why there are two ways in which we can connect the ports to the external signal. Okay. So any other queries? Okay, so I'll proceed. Now another provision is there that we can write our module code and then we can simulate our code to check whether the code which we have written is working as per as the need which we have designed it for. Right. Okay. So Rajesh, check 1 minute. For which are you asking the doubt? Over here, the variable is s, right? So when I call it, I will give dot of s, and then the actual value which I'm passing, it is s underscore 1. Of this one or over here? You're talking of this or you're talking of this? Okay. So I'll just repeat once more. When I'm calling it by this method, I will call dot of s. Okay, what variable it is and what value I'm passing it, I will give s underscore 1 value I'm passing, so I'll give s underscore 1. And in this method, I don't need to write in that particular order as was defined. Okay, so we can define the number as an integer, we can define it as a hexadecimal number, or we can define it as a binary number. So what is binary number? This is either one or zero. Okay. So this 3 over here implies the bit size, how many bits it is taking. Okay, if we write 4B1010, so we are saying to our compiler that this is a 4-bit number and it is represented in binary form and it is 1010. Okay, so then it will compile it and it will proceed. So this is, we have to define the bit size, how many bit sizes, etc. We will define. Similarly, 4D4 is like it's a 4-bit decimal number with the value 4. Now, if you want it to be hexadecimal, okay, if we want it to be hexadecimal, so hexadecimal number is what? It can take from 0 to E. No, it can take 0 to F. It can take 0 to F. So, like A, 0 to F, it can take values. So 0 it will consider 0, F it will consider as 15. Alright, so in a hexadecimal thing, hexadecimal is used because it can represent 4 bits. Okay, 4 bits at a time, it will represent by a single value. So if we are saying it's hexadecimal, let us assume the smallest hexadecimal or very small, or size, let us 8 comma hex. What does it mean is it is 8-bit. Okay, 8-bit hexadecimal it is, and the value we assign it, assume we assign it a value A1. Okay, we assign it a value A1. So what is this value in our binary format? So in binary format, if you would have written this will be 8 comma B, and A will take the value 10. So 10 will be 1010. So these all stand for A, and 1 will be 0001. Okay, so this is, so if it is in binary form, it will be written like this, and if it is in the hexadecimal form, you will write it like this. So hexadecimal form is like a compact form. A compact way we can write the value.
Sir, if I have written as 4-bit D, the maximum number after D I can write is 15, right? 15.
Yes.
4-bit D 15. Okay.
Yeah. Okay. So this is the same. Okay, we will also use a register, and we call a register by reg. Now assume, okay, let us try this. Okay, so can you tell me what is 16H ACBD in the binary form? Can anyone tell me? How will I write this down as? So A, I will write it as 1010. Okay, C, I will write it down. C will be, A is equivalent to 10. Okay, C is equivalent to 12.
10.
No, 12 is 1100. Okay, 12.
B is 1011.
Yes. And D?
Yeah, 1011.
1101. 1101.
1101.
Yes. D will be 1101. Okay. So this is how it can be written in a compact form. So that's the advantage of hexadecimal. But it's the same value. The values remains the same, but we can write in a different form to save some space. Now we have a register. Okay. Now a register is like the place where we are storing a value. Okay, storing value, or we are storing our data. So it will hold the previous value. Okay, it will retain the previous value until we place a new value there. Okay, so we have to name our data variable. We have to declare whether it is a register or a wire, and we will see about that. and it can be declared as a scalar or a vector. So here reg7 underscore 0, what does it mean is the variable name is data. Okay, the variable name is data. It consists of 8 bits. 8 bits. Okay, so it will have it will have data 0 will have its LSB. There'll be data 0, there'll be data 4, then there'll be data 7. Okay, all these are the represent the bits of it. So my data will actually be like this. Sorry, will be 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is my data, and this will have like it'll all have either ones or zeros. Okay, so this is my most significant bit. Okay, my most significant bit, and this one is my least significant bit. Right. So whatever values are stored in these boxes, that is in this register, and we have defined that register to have 8-bit register. All right. So reg 7 will have, so data 7 will have the most significant bit, and data 0 will have the least significant bit. So the register is basically used for storing our value. Yeah. Now we will see what is a net. Okay. Now a register, it cannot instantaneously change its value. It has, you have to, or based on a particular event. When an event occurs, then only the value in the register will change. It will change only when the particular event occurs. Sorry. Only when a particular event occurs, then only the value in the register will change. But if you want something which will change continuously, then we have to use a wire. A wire we have to use because if you want the value to change continuously. So over here, you see A is equal to B and C. B and C. So B and C are my inputs and A is my output. Now, what we want is the value of A should change anytime there's a change in B and C. We want the value of A to change anytime when there's a change in B and C. And so for that, we have to define the variable A as a wire. Okay. So based on that, whenever there's a change in B and C, the A value will change. But for a register, it is not possible for it to happen like that. Only when one particular event happens, and then we assign it a value to the register. Okay. So if you see, so now that's why we cannot use a wire, like a register cannot act as my input port. A register cannot act as my input port to a module because we don't know what value will come and when will that value change. Okay, it cannot be used as an input port. For the output port, we could use a register or we could use a wire. Okay, because the output, we are defining it on our terms. Okay, for output, we are controlling the output. Like the inputs might change, but we have defined how the output will change based on how the input changes. But the input, we have no control based on the external code and external modules, etc. What values are passed to the input is not in our hand. So that is why for an input, you will have to use a wire. Okay, for an input to a module, to a particular module, the input should be for the wire data type. Okay. Yes. So, like how in a module we include
Sir,
the
it
inputs.
is not clear, sir. Why register cannot be taken as an input for a module?
Okay. Let us assume we have a module. Okay, this is my half atom module. This is A, this is B, this is my sum, this is my carry. Okay. Now the input to A will be something like this. Okay. My input to B also will be something like this, suppose. Okay, it is not, I don't know when A will change from the value 0 to 1. I don't know. It is just something input coming. Okay. But for a register, only based on some particular event, we assign it some particular value. Okay, so when this is happening, we don't know. Okay, so that is why we don't use a register data type for the input.
Okay, sir.
So whatever are the registers, whatever are the wires, we will write up the list. And then whatever modules we are calling, we will call it by the module name, and we give that module which we are calling some name. Like we were using half adder 1, half adder 2, etc. So like that we give those names. Okay, so this meeting will end in around 5 to 6 minutes. So when the meeting ends, I will again resume and start this meeting. Okay, so then please join back that time. Okay. These are the things. See, now we are assigning some value. Okay, we are assigning a particular value to this out based on the AND of A and B. Okay. Now what we are doing over here is this right side. Right side is A and right side is B. They can be scalar or vectors. So scalar means A is just 1 bit. Okay. Or it could be defined as a 4-bit vector, etc. It can be anything. Okay. And this output, it cannot be a register. Okay, the output cannot be a register because what is happening is this output value is changing as and when A and B are changing. So this value out gets updated as and when A and B is changing. And so that is not possible for a register data type. Okay, so that time we have to use wire data type. Then another thing is we have something known as assigning a variable. Now to assign the value to a register, we will use this procedural assignment thing. Okay. So in procedural assignment, it is simple. There are two types. It can either be blocking or it could be non-blocking. So if we have these registers, we have defined registers A, B, C, etc. Okay. Then we give A value 10. We give B value 20. Okay. C value 40, etc. Now what I do is if I write A is equal to B, okay, B is equal to C. So at the end of when this entire code is executed, at the value A, I will get 20, at the value B, I will get 40, and C remains as it is. Okay. Why is it happening? Because first this is executed, then this is executed, then this is executed, then this is executed, then this is executed. Okay. But for the non-blocking assignment, suppose it was written A less than or equal to B, B less than or equal to C. So at the end of this, when this code is run, when it comes to this line of code, what will happen? Instantaneously in A, the value of B will go, and in B, the value of C will go. So A will be updated with the value 20, and B also, B will be updated to value 40. No. Okay, let us also put C is equal to A. Okay, if C is also equal to A. So C will get the value 10. But in case it was over here, C equal to A, then C will get the value 10. So both it is happening the same way. Okay. 1 minute.
It depends on the timing interval, right?
Yeah,
Like
it
10
depends.
nanosecond after that.
Yeah, it depends on the timing interval. But what actually happens over here is first this gets executed, then this. I think I have not chosen the correct example. So what you must remember is this will first happen, then this will happen, then this will happen. But in this case, all of them will happen simultaneously.
Yeah.
No, so yes, this now I realize my mistake. So over here, if in this line of code, what will happen is A will get the value B. So A will get the value 20. B will get the value C means B will get the value 40. Now C will get the value A. Now the value of A has now been changed to 20. So that's why C will get the value of 20. Any doubts in this part? The first part. I made a mistake here. C will get the value 20. We have defined the registers A, B, C. We have assigned their values. Now we are assigning it using blocking statements. So first we put A is equal to B. So A takes the value 20. Then we give B is equal to C. So B takes the value 40. Then we say C is equal to A. So when C is equal to A, what does it mean is now the value of A has been changed to 20. So it will get C will take the value 20. Okay. But in the next
Sir,
case,
is that first example is the same as wire?
no, it is a register. No, they are all registers. A, B, C are registers, right?
Okay.
Now, in the second case, what is happening is it is assume this line of code was removed. Okay, this line of code is removed. Now, from here, it is directly going here. What happens is, and there will also be some particular event at which this line of code will be executed. So, when that event occurs, what will happen is A will get the value B. Okay, so A will take the value 20. B will get the value C. That means B will get the value 40. C will get the value of A, but it will be the previous value of A, not the updated value of A. So C will take the value of 10. So what happens is all these commands are executed parallelly. Okay, they're executed at the same time. In the previous case, first this command was executed, then this command was executed, then this command was executed. But in this case, they will be executed parallelly. Okay. So blocking means when this line of code is happening, then the next line of code will only start being executed after this line of code has finished. Okay, so once A equal to B is done, then it will go to B equal to C. But in this one case, they all will happen simultaneously.
Okay.
Yeah.
Sir, if I write as a combination of like A equal to B and A less than or equal to B, in that manner, I clubbed this blocking and non-blocking, then how it gonna execute?
Then first you have written A equal to B, right? So it will first run that code and then it will run the next set of code. So first
sir, I didn't get your point, but I want like if the code contains the mix of blocking and non-blocking lines of code,
okay. No,
then how it gonna like
okay.
I have A equal to B is the first
Yes.
line,
Yes.
then A less than or equal to B,
Okay.
then C equal to B.
Okay.
This is my case.
But then you have given it in that sequence, right? So it will occur in that sequence only. See, you have written A is equal to B. Then you have written A is less than or equal to B. Okay. Then you have written B is equal to C. That means it will occur in this sequence. But suppose if you write B is less than or equal to C over here, then A and this code, this line of code and this line of code will be executed simultaneously at the same time. Okay.
Oh. Like up to which the blocking is blocking line arrives, then that up to that to top will execute at a stretch, right?
No, then this line will be executed, then this line will be executed.
Oh.
Okay.
Sir, which version of Xilinx are you are using, sir?
I don't remember exactly, but I actually downloaded the latest version. And the issue for me is
Okay,
I'm
but
using
what is your
Windows.
Windows?
Mine is Windows 11.
Windows 11. But I am facing issue with the Xilinx 14.7, sir.
Which Windows version you have?
Windows 11.
Okay, so you have to like run it in that virtual machine thing, right?
Yes, sir. That thing I need. Like something like a Windows 10 and Win 11. That's
No,
thing you are
no.
talking.
I just show you one minute. Yeah, my screen is visible, right? So this is my
Yes, sir. Visible.
so when I the Oracle VirtualBox it also installed and this also it installed. So this is my Xilinx. Okay, it is opening. One
Okay.
minute. Just hold on. So what about others? Others have you installed Xilinx and are you using that?
I have not installed, but can you able to share if you have time in this meeting how to install? Like if we already there any PPT kind of.
I actually don't have any PPT, and I
Actually, in
just
the last week session, Tejas sir explained how to install.
okay. Actually, that was for Windows 10. So Tejas sir sent me that
Okay.
I couldn't use that because mine is Windows 11 that way.
Yes, sir. The same problem with me
Uh,
too.
so I had to search online and I had to do actually that way.
Yes, sir. Have you
I
searched online, sir?
Yeah, I don't remember the video I referred to. That's the issue. So I had
Okay,
searched
sir.
online and saw Windows 11 how to install, and I had followed those steps. What you have to do.
Okay. Sir, if possible, please share that link if possible.
Okay.
Actually, I'm trying to install the same with a IT guy.
Okay.
He said that he needs time.
Okay. Okay. Actually, so you need that installation. But the others, Rajashekar and all that.
Sir, I'm using Windows 7, sir, installed.
Oh, you installed it. Okay.
So, sorry, Windows 10. Sorry.
Okay. Yeah. So like this, I was
I
able to make. Yes.
I am Windows 11 only. Mine also.
Okay.
Mine was Windows 11 only.
For you, it will be a bit difficult. Yes. Yeah, but online that video, some video I don't remember which one I referred to. So that I used and I was able to do it. So I'll try to find out and I'll try to post that link also on the YouTube video which I upload. Okay. So
Sir,
yes.
sir, in the last slide,
Mhm.
that blocking and unblocking,
Non-blocking. Yes.
sir, wherever we are seeing that the blocking statements, all those assignments will be made sequentially,
Okay.
right?
Yes. Yes.
Similarly, wherever we are seeing this non-blocking
Mhm.
symbol, the
Mhm.
assignments will be made parallelly.
Yeah, they'll be made parallelly.
So,
Like even
okay,
actually,
sir,
right?
based on
Actually, what Banerjee asked, even I am actually getting the doubt. Like he told if A is equal to B, then I do A less than or equal to B, B less than or equal to C, C less than or equal to A. Suppose I do. Then I put B equal to C. Then again I put A less than or equal to C. So I think Banerjee's doubt is whether this and this will occur simultaneously.
Yes, sir. Exactly.
So even like I think this we'll have to simulate and check. To what I can understand is first it will run this set of code because it is blocking. So it will run this set of code, then it has to go to the next set of code. And because all these are non-blocking statements, it will assign it will perform all of them simultaneously. Then once it is done that, it will go to the next line of code. So it goes to the next line of code and it will perform this. And then it will go and it will perform this. This is what I'm thinking, but I think to verify this, probably we'll have to simulate it only.
Yes, sir. But the issue is like these non-blocking. I'm thinking there may be a chance that all these non-blocking may execute at a stretch.
Yeah, that's the doubt. We'll have to actually simulate and check actually this one.
Okay. Okay, sir.
Okay.
Sir, like, is there, sir, in MATLAB there will be debug, there is an option to break that loop, like something debug, something is
Yes,
there,
yes.
option. Will there same
Sir, actually,
option
but here
available in
there's
Xilinx too?
Okay, one time. So I have not used that thing. Okay. So I don't know. Like you're talking about putting those breakpoints, right?
Yes, sir, exactly.
Yes. So that I haven't actually used till now. So it's you can check online that way. Okay, Rajesh Sekhar, you were saying something?
sir, in this example which you have written,
Mhm.
even though there seems to be parallel execution, but the value of A there seems to be a conflict.
Oh, which example I have written three? So
No, the first four lines: A equal
first
to
four
B, A
line.
less than equal to B.
Okay,
Yes,
yes,
sir.
yes.
B less than equal to C.
Okay.
And then the third line B equal to C. And then fourth
Okay.
line A less than or equal to C.
Yes, yes.
So in that, even though the second and fourth line executes parallelly, the A will have both B and C values. So such
If
kind
it
of error
was
may arise, I think.
these things here, if at all it happened, you'll have to actually see. The thing is, these Xilinx will make that sort of, those gates and the logic way how it is being executed. So that we'll have to see. Actually, I'll have to check this. Okay. I can't exactly tell. Can only be told after simulating. Sure. Then any other queries, or I can proceed?
Sir, proceed.
Okay. So we'll see structural modeling. So these are the basic gates, all of you know. Okay. AND gate, NAND gate. NAND is just the opposite of AND gate. Okay. All these things we know. Then we can also have a NOT gate, like a NOT gate. This is suppose A, this will be A bar. Alright. Now we can design a 4-bit adder. Okay. This is the example which Saurabh used. There's a 4-bit adder. So this 4-bit adder, like the ripple carry adder, okay? Ripple carry adder is there. What are the inputs? We have one input here, second input here, third input here. So this input, let us assume this input is A. Okay, this is input B. This is output S. This is output C out and C in. So A is a vector. Okay, 3 0. That means it's a 4-bit vector. B also is a vector 3 0. It is a 4-bit vector. Sum also is a vector 3 0. It is a 4-bit vector. Okay, this is C in and this is C out. Okay, this is our ripple carry adder. Now, this ripple carry adder is being broken down into 4 full adders. So 4 bits, so each bit 1 adder. Okay. So 1 full adder, 2 full adder, 3 full adder, 4 full adder. So the first, like you see, you have 1, 1, 1, 1. No. 1, 0, 1, 0, so plus 0, 1, 1, 1. What will it do? First, these two have to be added. Okay, so that is being done in this full adder. Okay, so this will be 1. And the carry which comes will be 0. Okay, there's no carry over here. And S which will come will be 1. Then these two are executed. 1, 1 gives output 0 and 1 carry. So here carry will become 1. This will have a value 0. Okay, then this carry will go over here and these two also will be added. So 1 plus 1 becomes again 0 with the carry. So this becomes 1. So carry 3 is 1, sum is 0. Okay, and again 1, 1. This will give value 0 and this has a carry of 1. So the output S will be 0, 0, 0, 1 and my carry out will have a value 1. Okay, so this is how this full adder, 4-bit adder is being implemented. And this implementation, we are breaking it down into blocks. Each bit into one block, full adder, full adder, full adder, full adder. This is for my LSP, this is for my MSP. Okay. So, yes. So,
Sir, one thing I didn't get, sir, a general doubt. How will
yes.
we get a carry for the first block?
Okay, that actually comes from the, see, just not like you're getting your, this, there are three inputs, A, B, and Cn. Okay. A is coming from the previous. So this A, B, Cn was the output of something else. And this is the input to my 4-bit ripple carry adder. Okay. And this is generating S and C out. Okay. So A
Oh,
and
like
B.
carry in the sense, sir, carry in the sense like in the microprocessors, like if there is an overflow
Yes,
like
yes.
that, there will be.
Yeah, the same concept. Okay. See,
Okay, sir. Okay, thank you.
microprocessor, FPGA, they're all these digital circuits. So they'll also have the same issue of carry and all these things. Okay.
Okay.
Yeah.
Like you are saying that this carry might be the overflow bit of the previous block.
Yes, exactly. And this out is the
Okay,
overflow of
okay.
this ripple carrier. Okay.
Okay, sir. Thank you.
Okay, so what they do is this 4-bit adder, we are using 4 full adders to execute it, 1 full adder for each bit, and the full adder is being executed by a half adder and an OR circuit. Okay. So this is how we are defining. So this will be one module. In this module, we will call 4 full adders. 4 full adders we will call. Okay. Full adder will call a half adder and an OR gate. Okay. Like that, they are broken down into blocks. Right. Okay. So this is just showing, this is the Verilog code which is there. So this is my, again, my inputs, 4-bit input vector, my input Cin. Similarly, I declare my sum 4-bit output, carry also, carry out. Okay, wires. Okay, these are defined as the wire nets. So why do I have to define these wires C1, C2, C3? Now what is happening is my full adder, like this C1, okay, it is an internal variable. It is not an output. C1 is not my output. This C out is my output. Okay, C out is my output. But this C1, C2, C3, they are just some internal variables. So to use those internal variables, I'm using wire. I'm using a wire. I'm not using a register. So what I am doing is, I am implementing the first full adder. The first full adder is given by this one, FA0. It takes the sum, it will give output S0 and C1. And A0, the LSB of A, this one, and B0. Okay. And it is taking Cn. Now this C1 is my input to my next full adder. Okay. This C1 is my input to my next full adder. So C1, then A1, B1, and then output comes S1 and C2. Okay. So in this similar manner, this carry of the previous full adder is propagated to the next full adder, etc. And we are writing the code for a complete ripple carry adder. All right. And we have to instantiate this. Okay. And so this full adder will be defined somewhere else. In another module, we have defined this full adder module, and the full adder module has its own internal code. Any doubts?
Sir, like here, sir, here FA space FA0 is written. Like, sir, are you going to show the full adder code too?
Yeah. Full adder code also is there, no? This is the full adder code. Okay.
Okay.
So in the full adder code, what is there? Full adder code has code for 2 half adders. Okay, full adder code has code for 2 half. This half adder 1, half adder 2. So this full adder is taking 1 bit. Okay, A is 1 bit, B is 1 bit, C also is 1 bit. So A, B is there. It goes to the half adder. Okay, from the half adder, generate some S1, C1, S2, C2, etc. Then those S1 and S2, S2 is the sum, and C1 and then this S1 over here comes over here, and that is used to generate S2 and C2, and the carry out is the OR of C1 or C2. Okay, so that's how we define. So my full adder has two half adders. So this is half adder 1, this is half adder 2, and this is my OR gate, which is used to generate my carry. So if you remember in that block which we had here, so my full adder will have two half adders and one OR gate. Okay, my 4-bit adder has 4 full adders. Each full adder has two half adders and one OR gate. All right. Any queries in this?
No.
Okay, so now how is the half adder being executed? So the half adder consists of what? A and B is XOR. Okay, XOR is there. This is a gate. So my S of my half adder is the XOR of A, B, and my carry is the AND of A and B. Okay, so these are executed by different gates, gate 1 and gate 2. And they are using the primitives of XOR and AND, which is already defined in Verilog. Okay. So now we will go to data flow modeling in Verilog. So we did structural modeling. Like we had one module and it had certain submodules also had certain submodules, etc. And that is how we have written our code to do the operation of a full adder. Now we are using data flow modeling.
Sir,
Yes.
sir, the instantiation means it is like a defining a module.
No, it is like giving that mode. No, can you repeat your question?
What do you, the instantiation means? Are we trying to define as a module, or?
No, we are not defining a module. We are calling that module. Okay, like it is. We are like that module. It's like a particular object. It's like an what do you say?
It's predefined.
Yes, it is a predefined. Like it's a predefined sort of like it's object.
Like we have to define the function, right?
Yeah, that see like this
Function definition and calling.
Yes, so here we are defining.
Yeah, that is okay, sir. But
yes, okay.
Yeah, that is okay. But
see, instantiate is like we are calling a particular function or calling a particular module. What we have shown here is this XOR gate and AND gate. We don't need to define them. We don't need to define them because they are already predefined. They're already predefined in Verilog. Okay, in Verilog they're already predefined. But my half adder is not predefined. So I'm going to define the function of half adder. Similarly, I define the function of a full adder and I define the function of a 4-bit ripple carry adder. Okay. So in the half adder, I am using already predefined functions. In the full adder, I'm using 2 half adder functions and 1 OR gate function. In my ripple carry adder, what I'm doing, I'm directly using 4 full carry adder, 4 full adders. So I have gone to the root level. So the root, I have to use my gates. Okay, and my gates I will use, which are already predefined. So I define my half adder based on that gates. Then I define my full adder based on the half adder and on a gate. Then I define my ripple carry adder based on 4 full adders. That is how we have, that is the structural approach. Okay.
Sir, then this command line instantiate XOR gate into the module, right? Okay. According to my understanding, I'm saying I don't.
Yes.
Actually, we are just calling. Okay, sir. Okay,
yeah, we're
that's
just calling
understood.
the function. Yeah, it is like a fancy name, but we're just calling the function to execute it.
Okay.
Okay. Yeah.
Okay.
Someone sent something. Mohan Krishna, like hardware prototype means of the PCB and etc.
Yes, correct. I mean, I saw the introduction course for this, where the course coordinators will help to build hardware for the interest of individual, with the interest of individual, and I will procure all the parts. So parallelly, I will make software and do in the same hardware proto also. But not now. At the end of meeting, if you have time, can you explain
Okay.
about that?
Okay, actually, others also had that doubt, right? They wanted to make the hardware and everything. So I had
Yes, sir.
searched a little, but I wasn't able to find any good boards for you to run, actually. So,
Okay.
like, what I would recommend is you make a, like, either you could make a PCB, but PCB is like a bit of a more complicated thing. Okay, it's a bit complicated. What you can use is you can use a Vero board. Okay, you can use a Vero board. Okay, it is recommended not, you cannot use a, like, what do you say, breadboard. Breadboard you
Breadboard.
cannot use because the power is more,
Okay.
right? The current is more, etc. So Vero board,
Hmm.
what is the Vero board you can buy? It will be like this. It will be like this. Okay, so these are your
Yeah, that
nodes.
brown color board
Yeah, brown color board. So you can make your
with the
connections.
holes.
Yes, and you can solder it from the bottom. Okay, you can make the layout and solder it from the bottom. The advantage of a Vero board is you can make modifications. Okay, you can make modifications as per your need. It will be painful to make this modifications that is there, but you can at least make it. But in a PCB, once you design it, it is very hard to modify. Okay. So my advice to you guys is you make a simple buck converter. Okay, simple make a buck converter. Right? Make a buck converter. Don't need to go for very fancy components, etc. Just make sure, like, the ratings are fine, current, how much it can carry, voltage, like some safety factor, all those things you take it into account. Make a simple buck converter with simple current sensing, which we taught earlier. And you can make you don't need to also make it very compact or anything. You can make it big. Okay, make it big. And you can run the converter at low frequency. Okay, low frequency. So if you run it at low frequency, like the effects of these like parasitics and all will be minimal. So that is what I would advise. Because see, if your objective is to learn, you want to implement these codes and logic, this board is secondary. Board is where you're going to, board is like you're testing it on that board. Okay, main thing is you want to learn your codes and logic. You want to check whether logic and codes are working. So for that, just make a simple Vero board, buy a Vero board, buy MOSFET, buy your gate driver, okay, and resistors, capacitors, inductors as per your requirement. Go for a simple buck converter, low power rating, maybe say 20 watt also is quite large, some small rating, and you run it, okay, and then like it will be good for you. Once you are confident of that, then you can go for higher things like a PCB or something else.
Yeah, Calvin, in
Yes.
course introduction, it was mentioned the bill of materials and schematics
Okay.
and our layout can be provided to the students. Are they available?
Actually, they are not provided actually. I'm not sure for that. So that is the thing. I'll have to ask again. Yeah.
So we try, sir. Yesterday also I talked with Vejagola sir,
What do you do?
but he told it is not possible.
Okay, okay.
Maybe at the next live session we have to ask the sir.
Okay,
We
yes,
asked
yes,
in the
yes.
previous session itself.
So
We asked in the
what we
previous
do?
session itself, but sir,
Previous session you asked what did sir say?
I think Vejagola sir talked with the sir and he replied
What did sir say?
in the meeting in the session, our PMRF session.
Yes, yes, yes.
That he's. I think that it is we have to make our own.
Oh, okay, okay. Then probably it won't be provided actually.
Yes.
Okay.
At least as sir said, as some other person is saying, At least the bill of the component names, ratings, and if the part numbers of the components are, if it is listed, then we can try, because there is too much components involved. I think, especially in the signal conditioning board and
Okay, yes,
I
yes.
don't. Yeah, buck converter, as you said, in Vero board we can purchase components and make. Temporarily we can make,
Yeah,
but
yeah.
for that we need only through hole components. No, sir. In Vero board we can use only through hole.
Yes, correct. So,
But in some, there are some part numbers in the bread in the PCB where they are using SMD devices also.
okay, that is there,
So,
but those ICs we're talking about, no? So ICs you can also solder it to the breadboard, to the variable. I mean, there also comes with the IC holder also there. So you can solder the IC holder and then you can put the IC on top of that. But that you'll have to check. Okay, that may not be possible for all ICs.
Yeah, but instead of parts, is there any schematics available? Schematics also is fine. You know, because for the design part, power converter or this control circuitry, we can do by, I mean, I can do by my own.
Yes,
But
sure,
if schematics is there, just like a startup, like a starting up,
okay.
okay, what to build, I will have complete idea for the whole circuit, what it require.
Okay. Actually, since they're not sharing it, my advice is there was this, I had conducted this current sensing, all those things I taught the previous week. So that
they,
week,
they said they didn't say they won't share, but their intention is we want to make our own.
okay. Achha. Okay, so actually, there in the they have provided in one of the slides, in one of the things it was shown about the schematic I showed last time. I had shown the schematic, right? Some parts of the schematic I had shown, if you remember, last session. I also uploaded that notes also. I uploaded actually some parts of the schematic were there, which were
The
there.
schematic you mean power board, sir?
Yes, like it's shown it, right? You can check actually in your previous lecture video as well as in the previous lecture notes. There is some parts of the schematic. It is not very clear, that I would say. It is not very clear, but there are some parts there. So that is available. You can work with that. So you guys are getting access to my videos and everything, right?
Sir, that is okay. Sir, but you said those handouts you will be uploading in the YouTube channel, but it is not uploaded, it seems.
Handouts, actually, there's a link is not there. The link was there. Okay, I will check that also. The link for my notes, right? Link to notes. I have uploaded a link to the folder to the notes. Okay, the link to the folder to the. I have uploaded the link to the folder where the notes are present.
Yeah, that folders are it is updated regularly, sir.
So there only the
Only
notes
that
are there.
Okay.
There,
So
like,
along with the slide, annotated slide, along with the annotated slide, you are saying it is there.
Yeah, no, I've only put the annotated slide. You don't want the annotated slide, you want the accurate slide. No,
Yeah, sir. Maybe, sir, because Tejagala sir is uploading both.
Oh, okay. You want both the slides, okay. I thought the annotated one was only what you guys wanted, so I was uploading only that. Okay. Both slides, the annotated one and the non-annotated, right? Okay. Gotcha. Okay. So, okay, we'll continue. We'll try to finish this at least. Yeah. So this also we are actually already seen. So when we are declaring like this, okay, this out is actually just a wire. Out is also just a wire. Over here also, it is like a wire only. Okay. Both are, we are assigning value and it's of the wire type. Okay, the wire type. Then, okay. So T flip-flop, we will not get into the particular details of it, but what you can know is a T flip-flop can be implemented like this. And this is how a T flip-flop is there. All right, and you can make it very simple. So if you have time, you can go through this and understand it. But what it is saying is, we are assigning these variables like this. Okay, these variables are all assigned like this. We are using all of them are as wire data types. Okay, they all are wire data types. We have defined over here that they are wire data types. All right, and when this module is called, these functions take place. This assignment will take place. Once we have defined the flip-flop, D flip-flop, then we can just simply use the T flip-flop to execute the D flip-flop. All right. So we don't need to actually reduce these T flip-flop or that. So I'll not spend much time over here. Now we'll go to behavioral model. Okay. Achha. So now there's an initial thing. Okay, it's like the initializing. We are initializing certain variables. Certain variables are there. We are initializing them with the values for the initial thing. And then always is like what blocks are like being implemented in a loop. Like if you have like there's a while loop, etc. If you have used microcontroller, we have something known as a while loop. So in a similar thing, the always one is thing which is in a looping fashion is there. Okay. These blocking, non-blocking we had seen. All right. So this is some example which also Sir had shown. So swapping out two variables. So now we will come to events. Okay, at one particular event, what we want to happen. All right. So let us see. This is the D flip-flop module. D flip-flop is there. Just Q, D, clock, and reset. These are the inputs to my. So D is my input. Clock is my input. Reset is my input to the module. So it is given here. My output is a register. Okay, with the value Q. So what I'm saying is, I'm defining in this module is always at this event. Okay, when the positive edge of a clock. So what is positive edge? So this is the positive edge of the clock. This is the negative edge of the clock or the falling edge. So when there's a positive clock edge of the clock, then I will begin. And in the begin, I will go into begin and I will check this. If my reset is, if reset, what does this mean? If reset is 1. So if this can also be written as if reset is equal to 1, then I will do this. I will give the value Q. I will give the value Q 1 prime B0. That is, I will give it the bit number 0. If not, I will keep it the original value. Okay. No, if not, I will assign it the value D. And I will end it and I will do end module. So whenever you do it, remember to write begin and end at the same time. That you keep in mind. So any doubts in this part?
No.
All right. So what is happening when this clock will come, then it will enter in and then this will be executed. So it is in the always block. Right. Similarly, a named event. Let us assume we have given an event name data underscore receive. Okay, there's an event like this. Okay, now assume there was a clock. At the positive edge of that clock, you will go into begin statement and you will check if my last data packet has been received, then I will set data underscore received, I will set it to 1. Okay, this will happen. Then when this data underscore received happens, what I will do is this data underscore buffer, I will put this data packet 0, data packet 1, data packet 3. What I will do is I will append them. Okay, I will append means like I will sort of combine them. So okay, so this event this event data underscore received is triggered. Okay, it is triggered by this. By this line, I am triggering that event, and using @, I am recognizing that this event has occurred. Okay, so the event is triggered by using this line. So this event is happening in my code. Okay, in my code, I'm executing my code, and when something has happened, when some condition has been achieved, then I will trigger that event. Okay, I will trigger it using this statement. And once that event has been triggered, then that triggering of that event is recognized by this @, okay, by this @. And once it is recognized, the code which will execute will come. Okay. So this meeting will end in 1 minute. So I will start the next meeting after that. Okay. So any doubts still in this one till now?
Yes.
Okay. Meeting will end 1 minute. So my screen is visible now, right?
Yes.
Now we can have another type of event, okay, where either, okay, this is my D flip-flop, D clock reset, right? Output is again a register, and there are two events, either the passage of the clock or at the passage of the reset. If any of these events come, then it will go into this line of code. So once the event comes, it will go into any of these events because we're using OR. So when it goes in, it will check if the reset is high, that means it will give value Q1, it will give Q0, else it will give the value QD. So this is like a D flip-flop, okay? It has output Q, it has a reset, it has a clock, and this is my input D, okay? In the previous case, in the case 1, what is happening is only when the clock signal is coming, when this signal is coming, then only it was checking this, okay? It was checking this. So assume there was a state where it was like this, okay? This is my clock, this is my reset. So when the clock came, the reset was low. Then when the clock is not there, reset goes high and again falls off, and then the clock comes. So in the previous case, what would happen? This reset would be ignored. Okay, it would be ignored. But if we don't want such a thing to occur, then we want it to consider both the clockage of the clock as well as the reset. Then we have to give this line of code. Okay. So that's why it is known as a asynchronous reset D flip-flop. It is not synchronized with this clock. It happens when this event is happening. But if it was in the case, this is for case 3. In the case 1, this reset would have been ignored. Okay. It would have been ignored. But if it comes at the rising edge, then the reset would be done for case 1. That would be done for both case 1 and case 3. But in case 3, this part also is taken into account, which could be missed in case 1. Okay. So now we saw 4-bit triple carry counter, etc. We proceed to number systems. So as I told, okay, the number could be, this is for binary, this for hexadecimal, this for decimal, for octal it is something else. Now the types of binary numbers can either be straight binary, that means it is only positive, it takes only values positive, or it could be these two can take negative and positive. Okay, so these two binary number representation can take positive as well as negative values. Okay, so can anyone tell me what is the value of this? Assume it is a simple binary number. What is its decimal value?
22. Oh, sorry.
Yeah, 22. Okay. Now, this is a 5-bit number. Okay, this is a 5-bit number. So it can take value from 0 to how much?
2 power 5 minus 1.
So that is 31. It can take value 0 to 31. But it cannot be used to represent negative numbers. Okay, negative numbers cannot be represented by this. So if I want to represent negative numbers, I have to use 2's complement or offset binary. But the issue with 2's complement and offset binary, I will tell. For this, if in case it was 5-bit, the range is 0 to 31. While in this case, the range will be minus 16 to plus 15. Similarly, for offset binary, it will be minus 16 to plus 15. Okay, why? Because half of it we have to use to represent the negative values and another half for the positive values. Okay. Any queries in this?
Sir,
Yes.
Sir,
Mhm.
sir, I
sir,
don't
in
know
this
why we
offset
can't
binary,
represent.
what is the difference? 2's complement and offset value.
Okay, I'll tell that. I'll tell that. Next, Banerjee, you were saying something?
Sir, like, why can't we represent from minus 15 to plus 16? Like, plus 16 anyway can't be like represented like 2 power n minus 1.
Actually, they use the MSB bit, which is, I don't know, based on what people have taught the previous time, but
Okay.
they have taught. But the MSB is used to represent the sign. Okay, and if it is negative, it will be represented by
It
1.
is 1 means negative, I guess.
Yes, E1. That is why it holds the maximum weightage, and so the negative has a higher value. Okay, so that we can work with it. That has been used and it is being continued. Okay. So next, is a table I made. Okay, to help you guys understand. This is like a table, huh? For 3-bit. So this is my B2 is my MSB, B0 is my LSB. Okay. So what is when it's all zeros? Yeah, this is straight binary means it is unsigned. Unsigned means it is only positive. It can take only positive values. So because it is 3-bit, the value will range from 0 to 7. While in the negative one, it will range from minus 4 to plus 3. Okay. So, and how actually it is done? How do I get this number 7 or any number? It is for a straight bit, it is B2 into 2 raised to 2 plus B1 into 2 raised to 1 plus B0 into 2 raised to 0. This is for my straight binary, which is always positive. Okay. Any queries in this part?
No, sir. We don't know exactly about the offset binary.
Who has complement, you guys know? Like, 2's complement, it is just minus 1 into B2 into 2 raised to 2 plus B1 into 2 raised to 1 plus B0 into 2 raised to 0. So this dominates and this is the sign one. Okay. So
Sir, like, still
yes,
not
yes.
clear with the offset binary
Okay,
thing.
yes. Okay. Now we have 2's complement. Okay, we have 2's complement. Assume you have, so 2's complement you can represent a negative number. Now we want to convert 2's complement to offset binary. Okay. If you will observe, in 2's complement offset binary, the only difference is the sign is one of the MSB. Okay. For offset binary, if it is negative, the MSB will be 0. and if it is positive, the MSB will be 1. Assume I have represented a number. Okay, what is the representation for -3? In 2s complement, -3 is represented by 101. Now I want to, this is for 2s complement. Okay, I want to represent in terms of offset binary. So what I do is, I just flip this 1 and make it 0. So it becomes 001. And if you see 001 in offset binary, that is -3. Okay.
Sir, please repeat it once.
Yes. Okay. 2s complement, I represent -3 by 101. Okay. Now I want to represent -3 in offset binary. So what I do is, this MSB, I flip it, I invert it, so it becomes 001. So this is my offset binary.
Sir, flipping means how you got it?
Yes, if you see 001 for offset binary, 001 is -3, right?
Yes.
Yeah, so that's all. Just the MSB of a 2s complement, I just change that sign.
Okay, you are changing the sign of just MSB.
Yes, no, I'm just inverting
That like complement of
the
just
MSB.
MSB.
That's all.
Okay, sir. Okay. Thank you, sir.
Okay. Yes.
For representing negative numbers, there are having complement.
Sorry.
For representing negative numbers, we are having 2's complement form already.
Yes.
Then, sir, what is the application? What is the need for offset binary?
Okay, what is the need for offset binary? So that means yes. Actually, if you see for our ADC, will convert the input to 2s complement, and when we give that digital value to my DAC, it requires in the offset binary format. Okay, the DAC which we use requires the data in offset binary format. That is why we are learning that. Okay.
So ADC will convert binary into the offset binary.
No, my ADC will convert it into 2s complement. Okay. And then it will go through my PI controller, everything, etc., and it will give some digital value. Okay, that digital value I have to convert it into form of offset binary, and that offset binary I will send it to my DAC. Okay. Is someone saying something? No. Okay, so we proceed. So these are how we can represent data, like straight binary, 2s complement, etc. So as told. So just assume, you guys know now how to convert from unsigned to signed, everything, right? 2s complement is what? Suppose this 1011. Okay, this is my data. This corresponds to value. How much is the value?
11.
Yes. So in 2s complement, what I'll do first, I will invert this. So this will be 0 1 0 0. Then I will add 1 to it. So this will become 1 0 1 0. So this is my 2s complement. Okay. This represents my 2s complement. Alright. So now we will proceed further. These things were told. Okay. Now my ADC, as I told, there's a supply to the ADC. Okay, that supply can be ranging from either -1 to +1, or it could be 2 to 0, etc. So assume my ADC can take the ADC which is there, can take between -1 to +1. Okay, it can read these analog values. All right. So my span of my ADC is 1 minus or minus 1, that is 2 volt. Okay. And also the ADC used in the board is a 10-bit ADC. Also, it is actually a pipeline ADC with some six cycle delay, etc. That is there for the ADC. So, okay. Now, 10-bit ADC means it's of this format. Okay, it is of this format. This is my 10-bit ADC. So what is happening is 2 volt will have B9, all these values to be 1, 1, 1, 1, 1. Okay, this will be 2 volt. No, sorry, this will be 1. Wait a minute. I'm sorry, so this thing 0 to plus 2 is 0 to plus 2. So 2 volt will have all 1, 1, 1. Okay, 2 volt will have all 1, 1, 1. If we have 1 volt, it will be half. So what will be the half of this? Can anyone tell me what will be the half of this?
It is 0 and remaining ones.
No, if it was 0 and remaining ones, then the value just change. This is not the correct one.
No, sir.
B9
1
will be
and
0.
remaining all zeros.
So
So 1 in the MSP and all zeros.
all zeros. Okay, so that is how we represent it. So similar. So in this
Sir,
fashion, yes.
Sir, V-span is like only input voltage or the supply voltage?
It is a supply voltage. Like how much is the supply voltage? That much only it can take, right? That much values only the ADC
V-span
can
is, sir, you are saying that V-span is the V supply voltage.
Yes, yes, yes.
The range. But
The
you
range.
are saying V min to Vmax is different from the V supply, right?
No, actually I made an error. It was V minimum is 0, V max is plus 2. Okay.
Okay. Sir, will the resolution of ADC, in the last class you have mentioned that the resolution of ADC depends on the supply voltage to ADC.
Yes, yes, exactly.
But here you are saying V into Vmax is just the input voltage range.
No. Actually, see, let's suppose this is my ADC. Okay, it is being supplied by 3 volt and 3 volt, and this is ground. Suppose let's take the simple example, single-ended ADC. So if I give a value of 2 volt, it will convert it into a digital value. If I give value 3 volt, it will convert into a maximum value. Okay, that is full all ones. If I give it 0 volt, it will convert all zeros. Is that part clear?
Yes, clear.
But if I give value 3.1 volt, what value will it assign? Because already all ones is assigned to 3 volt. What will it assign to 3.1 volt? Okay, it cannot assign any value to it.
Yes.
So it will assign only 1, 1, 1, 1. Or possibly the ADC could also get damaged. Okay, the ADC also could possibly get damaged. See, these are like, these are all these ICs. Okay, ICs. They have all these pins, etc.
Yes.
They are very sensitive. They have some particular range in which you can apply values. So sometimes
Yes,
that
sir.
range could be dependent on the supply voltage. It could be that only V supply plus 0.01, not 0.01, like 0.1 volt, etc. is tolerable at that pin. If a supply voltage, like if the voltage at that pin goes higher than this value, then that pin will get damaged. If it's damaged, IC is gone. Okay. So that is why when we are choosing the ADC, and we must make sure that this input to the ADC lies within the supply range. Okay.
Okay.
Supply defines what is the permissible range, not the input does not define what is the permissible range. So my supply defines what are my permissible input range to the ADC.
Okay.
Sir,
Yes.
sir, here suppose in this case supply voltage is 3 volts and we are given 2 volts at the input at the maximum. Then will you take any intermediate digital value or 111?
No, see, if 3 volt was my supply to my ADC, and I give input 2 volt. Okay, I give input 2 volt.
2 volt.
Then
we are giving maximum of 2 volt.
No. The Vmax is dependent on V supply. Okay. Vmax is dependent on V supply. Now, in this case, if supply voltage is 3 volt, then Vmax is also 3 volt. I choose V supply 2 volt because it is the one being used in this board.
Sir, you are saying that vSpan is exactly depends on the vSupply itself, right?
Yes, yes.
Sir,
Okay.
but
It
but
does not
no,
depend on the input range. Like whatever you are giving, just if I am getting 0 to 2 volts and the supply is 3 volts and the bit size is fixed, then the resolution of ADC doesn't change.
No. Resolution of the ADC depends on the supply voltage, not the ADC. Let me just tell
Yes, sir. Supply voltage is 3 volts fixed.
Assume it is 3 volt, yes. Okay.
And the ADC is 3-bit ADC.
Okay. Yes.
Whatever the input we are giving, it doesn't matter. In this case, the resolution of ADC is fixed. That is 3 by 2 cube.
3 by 2 raised to 3, that is around 3 by 8. Yes.
Yes, that is the ADC, resolution of ADC.
Yes, 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 exactly, yes.
Okay, sir. Okay, then it is clear.
Sir?
Yes.
If sir, if the supply voltage is 3 volts and if the maximum voltage is desired by the supply voltage, then there is no chance of giving 3.1.
Why?
Because supply voltage is at 3 volts.
Okay, wait. Let me just see over here. Okay, this is my ADC, right? This is connected to 3 volt. This is connected to my ground. If I apply 0.1 volt, suppose this was a 3-bit ADC. Okay, let us assume 10-bit ADC. Okay, 10-bit ADC. So the resolution of the ADC is 3 by 2 raised to 10. That is approximately 3 millivolt. Okay. So this 0.1 corresponds to 100 millivolt. So it will map this 100 millivolt to around 3 into 33. So it will map it to around 33, value 33, digital value 33. Since it is a 10-bit ADC, the maximum value it can give is 1024. So apply 0.1 volt, I get 33. If I apply 3 volt, I will get 1024. Okay. If I apply 1.5 volt, I will get 512. Okay.
Yes, sir. Yeah, this is understood, sir. But if the input is 3.1 volts, there is no possibility of happening that much.
It will detect it as 1024 only, no?
Yeah, it will detect, but because since the input max voltage depends on the supply voltage, the supply voltage stands at 3 volt, this won't go above 3, right, sir?
Yeah, it won't go above 3 volts. Okay, so now we will consider the concept of Q format. So till now we were just seeing integer values. Okay, it was either positive integer or negative integer. But what if we want to represent minus 3.5? Or let us start with plus. Okay, I want to represent plus 3.5. But till now my okay, this is unsigned. Till now I was just saying 0, 1, 2, 3, 4, 5. So I want to represent something between 3 and 4. Assume this is a 3-bit. Okay, assume it is 3-bit data. Okay, 3-bit data is there. I have B2 into 2 to the power 2 plus B1 into 2 raised to 1 plus B0 into 2 raised to 0. Okay, if I want the value, so based on the value of the bits, I will get that corresponding value. Assume I give 1, 0, 0 over here. Okay, 1, 0, 0 over here. What will I get the value to be equal to 4? Assume I give it a value 0, 1, 1. I will get the value to be equal to 3. Now, we will use a concept in which we want to add a decimal point. What we will do is we will scale it as B2 into 2 to the power 1 plus B1 into 2 to the power 0 plus B0 into 2 to the power minus 1. So what we are doing is we are dividing this by 2. I'm dividing this by 2. So I get it to be of this format. So if I apply to this, I apply 1 over here. Okay, assume I apply 1 over here. I apply 1 over here as well, and I apply 1 over here. So value I get is 2 plus 1 plus 0.5. That is equal to 3.5. Okay. Any errors and any questions in this?
No, sir. No. It's clear up to now.
Any other people have any questions? Okay, if not, we'll proceed.
Actually, here
Yes, tell.
actually we are here trying to accommodate the analog decimal values into our binary representation.
Yes, yeah. So, to some extent only we can represent it, and how accurately we can represent it depends upon the bit size. Okay, how many bits we have. So this has been represented in the form of Q 2.1. So we have 2 bits. These bits are before the decimal point and 1 bit after the decimal point. Okay. So I proceed. Yeah. These are bits. So assume this. Okay. Now we'll go for a signed number. A signed number. Okay, I want to represent, assume I want to represent minus, like let us say minus 1.75. Okay, minus 1.75. So how will I represent minus 1.75? Assume I have 5 bits. Okay, I have 5 bits. So I will give B4 into 2 to the power 4 plus B3 to the power 3 plus B2 to the power 2 plus B1 into 2 to the power 1 plus B0 into 2 to the power 0, and there will be a minus 1 over here. Okay, so if this was the representation, I would get the maximum value to be 32. So the range is from 0 to 32. Okay. Now I want to get.
Sir, here minus sign of how we are getting, sir. Will there be any additional bit for that?
Sorry. This will not be minus anything. So this will be minus 16 to plus 15. Minus 16 to plus 15.
Sir, like you are saying that this bit before is like I didn't get this point, sir. Minus 1 is external bit or something else?
No. When it was just unsigned, just a positive value, B4 is multiplied by 2 raised to 4. Right? B3 is multiplied by 2 raised to 3. And then they are added up.
This minus 1 belongs to which, sir? Only for B4
yes,
term or for the entire?
It belongs only to B4 term. So when minus 1 is there, B4 is multiplied by minus into 2 to the power 4.
Okay.
So now let me tell, if I have all of this, let us say this is 1. Okay, this is all 0, 0, 0, 0. So what I will get, minus 1 into 2 to the power 4. So minus 1 into 2 to the power 4 is minus 16. So that is my minus 16. Okay. Now assume B4 is 1 and B3 also is 1. So I will get minus 2 to the power 4 plus 2 to the power 3. That is minus 16 plus 8. So I will get a value minus 8. Okay. So in this fashion, I can get negative values.
Now, sir, now.
Yes, you see.
Sir, now if you go to the, instead of taking first 2, if you take the third one, then what will be the value, sir? Suppose if you take 1, 1, 1.
Take 1, 1, 1, right? So it will be minus 2 to the power 4 plus 2 to the power 3 plus 2 to the power 2. That will be minus 16 plus 8 plus 4. That will be equal to minus 4.
Sir, because we are trying to make decimal representation.
Yes, I have not yet gone to the decimal representation part. I'm just saying of the integer part. Okay. So first So is this point clear of the integer part?
Yes, sir.
Yes, sir, it is clear.
Okay. So now what I will do is I will put my decimal over here. Assume I will put my decimal over here. So what will I do? What I will do is I will divide by 2 raised to 2. Okay, I divide throughout by 2 raised to 2. So it become minus 1 into B4 raised to 2 raised to 2 plus B3 into 2 plus B.
Sir, before 2 raised to 3.
No, I divide by 2 raised to 2. That is I divide by 4.
Okay, sir. Okay.
So B2 into 2 to the power 0 plus B1 into 2 to the power minus 1 plus B0 into 2 to the power minus 2. Okay. Any doubts in this?
No, sir.
Okay. So now I want to get the value minus 1.75. So I have chosen a simple example, simple value. So I know how to do it. So it's actually what I have to do in this case is I will give this all I will be 1, 1, 1, 1, 1. So what will be, this will be minus 1 into 4 plus 1 into 2 plus 1 into 1 plus this will be plus 0.5 plus 0.25. Okay, till this part is it clear?
Yes, sir, clear.
Okay. So this gives me the value minus 1 into 4 is minus 4 plus 2 plus 1 is 3. So this becomes minus 1. Okay. Plus 0.75. I'm actually getting to be minus 0.25. There's some error. 1 minute. Okay, sorry. Yes. The value I chose was wrong. Okay.
No, the 2 power 2 we are divided by, but not of a negative.
Sorry?
Sir, we have divided the entire thing by 2 power 2, right?
Yes, by 2 to the power 2. Yes.
Sir, but on the negative side, have we done it, sir?
Yeah, I'm done it over here, right? Over here also I've done, right? Okay. Actually, this value I chose the wrong values. So let me just remove that. I chose the wrong values.
Which is wrong, sir, that 111.
This value is 111 is wrong actually. Some other value actually. Minus 1.75.
Sir, I guess the before bit is like dedicated for sign, and
Yeah,
there
before is
will
dedicated for
be.
sign. Wait.
Sir, then there won't be 2 square, right?
2 square
Multiple
is
of
there.
2 square
It
won't
has
be
to
there.
be there. It has to be there. So let me tell. It will actually be 1, 1, okay, and 1. So this will be 0, 0. So it will be minus 4 plus 2. That comes out to be minus 2 plus 2 raised to minus 2 is 0.25. So it comes out to be minus 2 plus 0.25. So it is minus 1.75. Okay.
Sir, please repeat it once.
Actually, last time I chose the wrong set of values. What values I should have chosen is 11001. So before I give value 1, so it is minus 1 into 2 to the power 4, so minus 4. B3 I give the value 1, so it is 1 into 2 to the power 1, that is 2. 0 and 0 multiply it, so I neglect that. So 1 into 2 to the power minus 2 is 0.25. So minus 4 plus 2 plus 0.25 becomes minus 2 plus 0.25. So it is equal to minus 1.75.
Sir, like here you have gone through this for minus 1.75, you went like this. If we
Yes.
have another set of value, then how to approach there?
Then you'll have to see through and find out actually exactly.
Sorry?
Like that you'll have to calculate it.
Like we have like LCM kind of stuff.
LCM kind of stuff that actually I have not used. Like through this way, thinking like this way, you can find out the value. Okay.
Okay.
Sir,
Yes.
sir, that 2 power 2 you are dividing, that is taken by the number of values after the decimal.
Yeah. After the decimal, yes.
Sir, if I want 0.01, like minus 1.0 minus 1.01 I have.
Then I'll have to increase the
Like
number of
for
bits.
this.
In this representation, I cannot get it. In this representation, I will not be able to get it. Because
Sir, how to decide that maximum value at the end?
That you'll have to increase the bit size in root. Okay. You'll have to increase the bit size in root. Here, if you see the range, the minimum value it can give 2 to the power minus 2, that is equal to 0.25. Okay. So I want to get around 0.1, 0.01, then I have to do by some 2 raised to minus x will be equal to 0.1, so something like this. 0.01, right? So based on that, I will get. So this will be 2 to the power x should be approximately equal to 100. So x will be log of 100 to the base 2. That we'll have to see in the calculator how much it is. Okay. So using some similar mechanism, you can get it.
Okay. Okay, sir.
Now,
sir, you have missed that. Sir, please, in the before slides, like here, Nmax, what is your intention to explain this, sir?
Nmax,
you are saying fictitious.
This is
yes,
just
sir.
a point. This is just a point. It is not necessary. Okay. This is not there. It's just for our
Okay,
understanding.
sir, if you have like 2 bits before the decimal point,
Yeah.
what is the maximum value I can give, sir? Like I have to take -1 into like B1
yes,
2 square plus.
Yes. So if you want a maximum value, then you will not give. You will give this value. You will give the value 0. Okay, 0 into the minus, because that is what is bringing your number down, right? The -1 is the one which is bringing it down. So that's why I give that value 0, and rest all values I give 1. So this will come out to be the very close. It will be approximately 3 point. This will be 0.125, 0.5, 0.625. I think it will be around 3.875. Okay, maximum value will be 3.87. Minimum value will be -4. So the minimum value if you want.
Sir, like in this format, you are writing in terms of signed bits, signed numbers, right?
Yes.
This representation is used for signed representation.
Yes.
Sir, is that the point like Q format is used for representing signed format? It's signed with signed terms itself?
No, it can be used to represent the unsigned data also, right? But
sir,
that time
for
we just put
unsigned
MSP 0. That time we just put MSP 0.
Yes. Overall, sir, if we are considering signed bit, we can represent both signed and unsigned, like positive and negative numbers.
Yes.
Can. Sir, is there any concept of like that we are not using negative numbers and I'm representing only from non-negative numbers? Is there any concept like that in Q format?
That I don't know actually. The practical thing we want both positive and negative, right? That is why we are doing it.
Yes.
So that's why
Okay.
I don't know about that.
Okay, sir. Sir, is that fixed?
Okay, are you guys able to see my screen?
Sorry, sir.
Yes.
Here in this case, it is 0, 1 underscore 1. The example that we have taken.
Yes.
Sir, here it will be first bit will be 1. It is anyway that 0 is representing -1, and then the second bit it is 1 into 2 to the power 0.
Yes.
And then plus 1 into 2 to the power minus 1. Sir, if you go by that way,
okay, yes. Here also I made a 1 minute, sorry. This will be plus 1.875, this will be minus 2. Minus 2, yes. Yes, this will be plus 1.875, this will be minus 2.
one is minus 2.
This is minus 2, and this is 1.875.
Okay.
Yes.
Okay.
Okay. Yeah, 2.8.
Sir, is this fixed Q points or floating?
No, this is fixed point. No, this is not floating. That is why we're doing fixed point, not floating data type.
Fixed in the sense, and fixed and floating differences I want to know.
Fixed and floating differences. Floating, like, it can take very minimal value. Such values very, like, it can go very accurate. Where if it's a 0.25.
Sir, are we going to discuss the same in this coming slides?
No, floating we are not using. Floating data type we are not using.
Okay, sir, please explain it once if we are not going to discuss.
Okay, no, like floating data type, it can go to a very minute value also. So there are some cases where you use floating data type and some places where you don't use floating data type. Okay, but the thing with fixed data point is, it's like guaranteed, sort of like if you multiply this by this, it will come out to be some particular value. But in floating data type, there might be some certain mismatch, etc. Like, I don't exactly remember, but I just once read one document where it told that there are certain dangers with numerical errors which can come if you use floating data type incorrectly. Okay, so that's why I think there's some particular reason why that's why they're using fixed point data type, but I don't know the exact reason.
Sir, fixed point in the sense, floating in the sense you are saying that is there any chance of moving that decimal point
Yes,
to the left and the
think,
right?
yes, I think in that sense it is floating. Okay. So we will go for addition in Q format. Suppose we are doing additions in Q format. What we will see is, let's take an example. We'll have Q1.3. Okay, Q1.3 is 1, 0, 1, 1. Okay, Q 2.2. So this is my point. So this is 0, 1.11. Now we want to add it. So what we will do is, this LSB will pad by 0 for this. So it will become Q 2.3. Now we want to make this Q 1.3 to be Q 2.3. So let us see what we do. So if there is a LSB, Q 2.2 we convert to Q 2.3, we just add a 0. And because we are just adding a 0 at the end, it is not changing the value. Okay, it is not changing the value. Now let us see the value of Q 1.3. Q 1.3, the value of this is 1.25. So it is 1.375. Okay, this one has a value of 1.375. Now I want to convert it into Q 2.3. So what I do is, this 1.011 is there. This is not there in the actual number. It is just fictitious. We're just showing it. What I do is I write it as 11.0. Sorry. I write it as 11.011. What will the value of this be? This was actually 2 raised to 1, 2 raised to 0, into 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3. So this is 2 raised to minus 3, 2 raised to minus 2, 2 raised to minus 1, 2 raised to 0, and 2 raised to 1. And this will be multiplied by minus 1. So this will be minus 1 into 2 raised to 1. So the value of this will be equal to minus 2 plus 1 plus 0 plus 0.5 plus 0.25, sorry, plus 0.125. So it will be minus 1 plus minus 1 plus 0.25 plus 0.125. Okay, so this will give me the value of minus 1 plus 0.375. That will be equal to minus 0.625. Okay, Acha, I'm really sorry. So this also over here also there'll be a -1. Let me correct it. So this will actually be Q1.3. The value of this is also, let me write again that actually done mistake. 1.011. Okay, this actually is 2 raised to -3, 2 raised to -2, 2 raised to -1. This is -1 into 2 raised to 0. So this will be -1 plus 0.25 plus 0.125. So this is also equal to -0.625. Okay. No, this is correct. Ah, yes, this is correct. Yes, this will be -0.625. So what we are doing is, yes.
We can't change from 1 bit to 2 bits, right? Like, and from 2 bits to 3 bits.
No, we're just adding those things. So we're just appending those bits, right?
Sir, if there are 3 bits, like we can consider only 2 bits. If there are only 2 bits, how can we consider 3 bits?
No, see, this in our digital platform, it might be limited only 16-bit or 32-bit. As long as we are within that limit, we can add bits. Okay. This is total 4-bit data, but my platform can support data up to 16 bits. So I can increase the data bit size, right?
Okay. Sir, if it itself it is like 16 bits and we are operating with 17 bits, then what?
It's not possible. It's not possible. It will throw in error. Okay,
you are saying that we can extend the bits, right?
Yes. But
Sir,
within the limits of the platform.
Okay. Here you are saying rest of LSB is padded with zeros and rest of MSB is extended by MSB.
Yes.
Could you please extend those 2 points, please?
See, in this case, it was Q2.2 was 01.11. Okay. 01.11. Now I want to convert into Q2.3. So just I add 01.1 and I add a 0 at the end. So that is padding with zeros. So value of this and value of this remains the same. Okay. The value of this.
Okay, that's fine.
1.75. Now for MSB, okay, actually I made a big error over here. So it is just what I'm saying is my value or number was 1.011. Okay, that was actually -0.625. What I do is you rest MSB's extend by MSB is what? I just add. I want to add one more MSB, means I just want to add one more bit. So what was the value in the MSB? Same value I add. So I'll put the value 1 over here. And rest of the numbers remains the same. They just remain the same. What is happening here? Initially, let us forget the decimal part, you leave it because that remains the same. What is happening is this one is multiplied by -1 into 2 to the power 0. So effectively it is getting multiplied by -1. Okay, it is getting multiplied by -1. So this is -1. Over here, it is getting multiplied by -2 plus 1. So that again comes out to be -1. Okay, so what I'm doing is just I'm extending the MSB by the MSBs. That's all.
Sir, if I add 0, like
then the number will change. Like if instead of here, if 1.011, I make it 01.011, then what will be the value?
It is 1.
It will be -1 into 2 to the power 1 and 2 to the power 0.
Like 1. It will be 1 plus 1.
Yes, that is not what I want, right?
Yes, sir. Like in this case, how adding 0 is not changing?
In the last case, here.
Yes.
Here, because it is here we have to add 1 because of the sign. This -1 sign is the issue. In the MSBs, the sign is the issue. That is why we have to add 1. But in the LSBs, the sign doesn't change. Okay, so that's why we add 0.
Okay. Okay, sir. Okay, it's clear now.
Okay, that is for addition. Similarly, if we are doing multiplication, what happens is these values get added up. Okay, they have to get added up. And sometimes we have to subtract it. We have to subtract one from it. Okay. So this is what happens when multiplication is there, and actually we have run out of time. But in the next session we will see PID controller, etc. So that time what happens is KP is multiplied by the error. Okay, KP is multiplied by the error. So that time we will see, we'll discuss about the multiplication. Okay, that we will do the next session. Okay. So I'll just wrap it up a bit fast. Okay. So in this week, also sir taught counter-based DPWM. Sir demonstrated it. Okay, he taught it and he demonstrated it. So this is used in voltage mode control. Okay. What happens is, this is my counter, and when my control value reaches the counter reaches that value, then it will reset my gate. It will reset it. Okay, and it will set it when the counter is 0. So this is my counter is extending up. It is a staircase waveform, and when the control signal value, and when the counter reaches the control signal value, it will reset it. Now, and we saw this was taught earlier now, how the clock signal is required. This is the T clock. Okay, so clock will be of such a high value so that put a limit in the resolution of the counter and etc. what we require, and we cannot have a very large N, because then the clock signal has to be a very high frequency, which is not possible always. So this is the counter-based DPWM. These all we had discussed earlier. So, so what happens is, this is my digital PWM. Okay, my digital PWM has 3 inputs. The count out is the output of my controller. My PID controller generates this count. Okay. FPWM is my clock for the PWM, and F clock is the clock for my counter. Okay, for implementing my counter. And QH is for my high side signal, and QL is the complementary with a dead time included, so that those switches will not have a shoot through. Okay. So the logic is what? My counter is incrementing like this. And when the controller output becomes less than the counter value, then this QPWM, which was initially high, goes to 0. Okay, that is the logic of this. And this counter is being updated at a particular fixed frequency. Okay. So that is at 1/f PWM. So this is the Verilog code which sir has written. So let us consider we are generating this DPWM. Alright, we are generating this DPWM with dead time. So I have my clock. Okay, I have my clock. I have my PWM frequency signal, clock signal also I'm giving. My controller output also is there. I have QH and I also have QL. So my clock and FPWM are my inputs to my block, and my count out also is my input to my block. Okay, the output of the controller, this also is my input to the block. And we are going to use 4.14. This is again this Q format. Okay, Q format is all there, which is there, and this is actually a 19-bit vector. Okay, this is a 19-bit vector data, which I'm representing 4 and 15. 4 plus 15 is 19. My output is QH and QL. That is the high side gate signal, and QL is the low side gate signal. And I'm using a reset net or wire I'm using for storing to know when I have to reset. Okay, to understand the condition of reset. Reset is when my count out, my counter becomes more than the reset, becomes more than this, then what will happen is my PWM signal, which was there, it has to go down. So it has to go to 0. Okay, so that is for my reset. This is my QPWM is there, and for a delay, which I want to implement, if I want to implement a delay, this is for my dead time. Okay, this is for implementing my dead time. Okay. So what I am doing is, my my counter, okay, my counter which I have, that is a 12-bit counter. Okay, it is a 12-bit counter. So what I'm doing to my 12-bit counter is, okay, and controller output is another variable, okay, which is a wire. So this controller output, I am giving it only the first 12 bits. I'm giving it only the first 12 bits of my count out. If you remember count out, you have a PID controller. Okay, you have a PID controller. It is generating a 19-bit data. A 19-bit data. But I don't want these 19 bits. I just want the initial 12 bits. What I'm doing is using this thing, 18:7. What I'm doing is my count out, which was actually 18:0. Okay, it had 19 bits. When I do count underscore out 18:7, I am neglecting 7 bits. So I'm effectively taking only the first 12 bits. I'm effectively taking only the first 12 bits. Why I'm doing it? Because my count out has to be equal to my counter number of bits. Okay, it has to be equal to my counter number of bits, which is again 12 bits. Okay. So this is what we are taking to the picture.
Then why complete bits are not taking into account?
In the counter, I told, right? In the counter, if we wanted to have higher resolution, larger number of bits, then the clock frequency would be very high, which might not be permissible, which might not be possible. So so we have taken a 12-bit count.
Hello.
Yes. Hello.
Okay, like there is a relation between clock frequency and the resolution. That's the thing.
Relation between?
I didn't get this point, sir. Why you are confining to 12 bits while there are 19 bits are available?
No, the counter has a clock to it. Okay, counter has a clock, and that clock has to be very high. The f clock will be of the range 2 raised to power n into my f of PWM. Okay, if my PWM is 1 megahertz and my bits is 2 raised to power 12, okay, then the value of 2 raised to power 12 is very high. That will come around, you will get around 4 gigahertz clock signal you will require, around 4 gigahertz. That is too high. Okay. That is why we have confined it to 12 bits. We are not FPGA.
Okay.
Then,
sir, if we are confining for 12 bits here, why you are taking 19 bits then?
Because the output of the PID controller is 19 bits. Okay, so that I will discuss in the next time when we are discussing voltage mode control about the PID controller. The output of the PID controller we will discuss a bit, and that turns out to be 19 bits. Okay. Once it comes in 19 bits, there are certain bits, the lower the LSBs, some LSBs we can discard. We are discarding some of the LSBs. Okay.
Okay, sir.
So now what we will see, if counter is equal to less than or equal to 1. Okay. What we will do, we will set the PWM signal to 1 and counter, we will increment it. And this is coming at a particular clock. Okay. So when this clock is coming, the clock comes here, that time we are incrementing the counter. Then the next case, there are certain other conditions. That is, the counter is less than the controller output. So this is my counter. Okay, and this is my controller output. This is my controller output. So what happens? And my QPWM is 1. And over here, it goes to 0. So as long as my counter, that is the staircase, is less than my counter output, I want QPWM to be 1. Okay. I want QPWM to be 1. But in case my counter reaches its maximum value, okay, the counter reaches its maximum value, which is 499. Then what will happen? I want my counter to go back to 0. Okay. And at that time, my PWM will still be at 0. Okay. PWM will still be at 0. And this condition is what happens when my counter, okay, when my controller value becomes greater than my counter. If it becomes greater than my counter, then what I have to do? I have to reset it. So that is given by this. So is this understood, or should I explain it once more, because this is very important?
Sir,
Yes, yes.
sir, once the controller attains the maximum value 490, the counter, and the counter reaches 490. Sir, after that it has to come to 0. At that point, if the controller value is greater than that, sir, can you explain just after 499 what will happen until it reaches?
Okay, so first I'll start from the starting. So counter value is 0. Okay, the counter value is 0. That's the first condition. The counter value is less than or equal to 1. That means the counter value is 0. Okay, the counter value has at one particular clock. Okay? This is always clock driven. So at this clock, the counter value, it is checking that the counter value is less than 0. Okay, it is less than 0. So it is less than 1. Okay, it is less than 1. That means the value is 0. What I will do is I will set to PWM, I will set it 1. Okay, then I will do, then at the next clock. Okay, that is why this always block is there. This is just always. This block determines only at my rising edge of my clock. I will go into this block of code and I will check. So always has come, or the positive edge clock has come, then you go into this begin. Okay, once it goes into this begin, it will first check. It first checks this if condition. This if condition doesn't happen. Then it'll go to the next condition. It goes to else if, goes to this condition. So if my counter is less than my controller output, this is my controller output. Okay, it is less than my controller output, then it still remains 1. So at this clock, it will check. It is when the next clock comes, it is greater than, it is not less than 1. So it will come to this condition. Okay, it will come to this condition. It will check if my counter is less than or equal to controller output, which is true. Then it will remain. Then it will check PWM will remain as 1. Okay, and my counter will become counter plus 1. Okay, so the counter becomes counter becomes 2 now. Okay, the counter becomes 2. So that will continue keeping on checking, and we'll keep on incrementing this, and PWM will remain the same. Then at this condition, okay, ignore this. Okay, ignore this for the time being. It has not, counter has not yet reached 499. Okay, counter is less. It is like, say, it is at this is 499. Assume this is, it is at 35. Okay, it is at 35. Till then, it just keeps on keeping the value 1. Now it reaches the value 35. Now, when it reaches the value 35, what happens is, this condition is no longer true. This condition is no longer true. So it will not execute this code. It checks this condition also is not true. It will not execute this code. So the else, the next option is what? I will bring QPWM, I'll bring it down to 0. I bring it down to 0. And the counter I still increment it. I make it 36. Then over here, 37, 38, what happens? This is not valid. This condition is not valid. Only this condition is there. So it will keep it, it will maintain it at 0. Then when it reaches 499, what it does is, when it has reached this value 499, my QPWM still be 0. Okay, it still be 0. Okay, my QPWM still be 0, and my counter value also is made 0. So at this clock, okay, at this clock, it will see that the value is 499. It will reset it to 0, and my PWM will continue to remain at 0. Okay. So I hope this is not over your heads. Hopefully.
Sir,
Yes.
actually, sir, the PWM, QPWM that we are giving, that we are getting out of this comparison, sir, that QPWM should have some minimum value.
Minimum value, like you're talking about this.
Ensure some minimum value of QPWM.
Okay, that we have not shown in this code, but that will be included later. Okay. You're talking that the duty ratio should have some minimum duty ratio, right?
Yes, sir.
Yes, that
to
is not
have vector operation to be done.
Yes, that has not been included over here, but that will be included. Okay, don't worry. See, over here, if I'm not wrong, this is your minimum value. So this, if you keep it as 10, okay, if you keep it as 10, it will remain that minimum value. Okay.
Which
Actually, if instead of if this was less than or equal to 1, I'd put the condition here, right? If in case it was less than or equal to 10. Okay, if it was less than or equal to 10, then it will always remain 1. Okay. Even if my controller output, suppose my controller output was here, okay, controller output was at 2, but my minimum value was 10. So even in this case, it will continue to remain high until it reaches 10. And once it reaches 10, this comparison will be made and it will be set at 0. Okay.
Okay.
Are you traveling in the train?
Yes, sir. Yes.
Okay. You're going home, huh?
Sir.
You're going home?
From home I'm coming back. From home I'm coming back to college.
Oh, okay. Right.
That's the craze your courses are having.
Oh.
That's why other what, sir?
No, Benaji was saying something.
Sir, we are really getting a lot of stuff from your courses.
Sir, actually, that I couldn't
we
hear the
didn't
other
get in
person
our
speaking because,
organizations too.
Okay, one at a time. Let Benaji say what?
Sir, we are getting a lot of stuff from your classes and courses.
Mm-hmm.
Those we are unable to get in our organizations. Like in our organizations, like it may take a longer time to understand the same.
Oh, okay.
Without the help of seniors.
Mm-hmm. Okay. Yeah.
Thanks a lot, sir.
Okay. Yeah. Okay.
Actually, we had this concept of queue format and all in our training sessions, but we didn't get the exact stuff. Like we have here, like there is a IEEE precision format, something else.
Okay.
That is being used in DSPs. IQ format, they say.
Okay.
I didn't get that concept during our training. I have to get into that concept with your basics that you have taught in this class.
Okay.
I hope I'll get clarity there.
Yeah. That's what.
Really happy with your courses, sir.
Okay. Actually, professor's course. Yeah.
Yes, sir, your sessions too helping us a lot.
Oh, okay. That's good to hear. And Rajesh Sekhar, you're saying something?
No, sir. I was saying I couldn't hear when other person was speaking.
Okay. That's fine. So now we will go to the last part of inserting dead time. Okay? We want to insert a dead time. So this is my QPWM. Okay. But if I just take the complement of it, it would be like this. Okay. This was the signal. And I just took the complement of the signal like this directly at this point. What the issue is, you see, if you go to a buck converter, you have this switch. This is your input. This is your complementary switch. This is your inductor, this is your capacitor, and this is your resistor. Okay, this is my diagram. This is your S1, this is your S2. And S2 is, this is Q, this is Q bar. Okay. When Q is equal to 1, Q bar is equal to 0. So this switch is on and this switch is off. Now at the instant, at the transition when this switch is turning off and this switch is turning on, what might happen is this off time, it will not instantaneously turn off. And this also will not instantaneously turn on. But a condition might happen where this is just not yet turned off and this is turned on. If that happens, what will happen? The entire current will flow through this. It will short circuit. And then that will damage the switches. So to avoid that, there's a dead time. What is a dead time is when this switch is turning off, I give a delay, and then I turn on the low side switch. And then I provide a signal to turn on the low side switch. So what is this? These are signals. Okay, these are actual signals. These are the PWM signals. So this is QH. So this is my QH is turning off. When it is turning off, it means my high side switch is being turned off. It might not immediately turn off. It might take some time. Okay, it might take some time. So I give time more than the time it would take to turn off. I give that dead time, and after that dead time is over, then I give the signal to turn on the next MOSFET. So even though I give the signal to turn on the next MOSFET, the MOSFET will not turn on immediately. It will also take some time. Okay, so this dead time is there to prevent both the MOSFETs from being on simultaneously. Okay. All right. So, yeah, so actually this was already drawn. I should have seen it. Okay. So we will just consider the concept of dead time. This is my QPWM. This is my QPWM signal. What I do is I just delay the signal by some time TD. Okay, that delay we generate using D flip-flops, etc. We just delay it. Okay, we just delay the signal. Assume it is done. I have delayed the signal through some logic code. I delay it by TD. Now what I do is I compare this signal and this signal. This signal I compare with this. So I AND those signals. So whenever, so what is my QH will be QPWM dot PWM underscore delay. So the AND, when I AND it, what will happen? This is 0 over here. During this dead time, it is 0. So this will also be 0. Here both are on, so it will be 1. Then at this time, extra time, which is for the dead time, one is on, another is off, so it will be 0. So that is how my signal will come. Okay, this is how my signal will come. Now for my QL, if I'm not wrong, it is XOR. So QL is XOR of QPWM and PWM delay. 1 minute. Let's see. Okay. This is the NOR of that. NOR actually. Okay. So what is happening is, you take the NOR operation. What is NOR? NOR, truth table of NOR is 0, 0. Wait. 1 minute. So when both are off, when this is 0, then this will be 1. When this is 1, this is 0, this will still be 0. Okay, when this is 1, this will still be 0. When this is 0, this is 1, still this will be 0. Only when both are 0, 0, then this will be on. Okay, this is my NOR table. So this is how I will get the signal for my low side. So this is my original signal. I delay it by some value, and then using simple AND gates, I get my high side PWM signal and my low side PWM signal. Okay. So any other doubts or queries in this?
I don't know exactly about the D flip-flop working.
Okay.
Like, if we are giving something like it gives with a delay, is that the thing?
Yes, it gives the delay.
The same data will be propagated to the output with a delay.
Yes, with the delay.
Okay. You are you are taking this delayed input and the original input and taking for QH and QL, right?
Yes, exactly. Yeah.
Okay, sir. Okay, thank you.
All right. So this is how we generate dead time. And this is the code. Okay, just the simple code. This is the and this is this for OR and NOR. Okay, OR and then NOT of it is NOR. Okay. So this is there. So if there are no other queries, we can end it for today.
Sir, I am finding difficulty in understanding these codes. Like there are even in the starting lectures, I found difficulty in understanding trailing edge and leading edge PWM. Now I am familiar with those concepts a little bit better.
Yes, fine.
Now I am finding difficulty with these architectures of Verilog. like you are saying event driven and like a blocking, non-blocking,
Okay.
like this stuff.
No. So like
Sir, like
no, tell.
okay, sir, tell me.
No, it will take time. Yeah, this will take time.
Okay.
And first thing I'd advise you to install Xilinx. Okay, that's the number one thing for
Okay.
verifying how it works. Okay, like so let's taught how to check, how to verify your code. Okay, once we do that, then it will improve.
Sir, is it like a C compiler? Just I can run and have the output?
No, should have seen such lecture like you have to write the code module, you have to create one by one. Then you have to
Yes,
check whether the module is correct, and then you run it, and then you simulate it. And when you simulate it, then you have to give those clock inputs. You'll have to give. You have to force some particular
sir,
constant.
like
Yes.
sir, simulating is like Simulink and this FPGA programming like M script, like
No,
that thing.
it's not exactly Simulink. It is actually like Simulink is also a graphical user interface for you, right? To run your programs.
Yes.
Similarly, this is also like simulator is like a graphical place where you can, give the sort of what you say, the test signals. You can define them, and then you can view it on a scope, like how you view it in a scope in MATLAB. You view it like that in the simulator. Okay.
Like, sir, the thing I got it like by giving the commands, I can get the graphical model, right?
No, you're generating the code, and then you go to the simulator, and then you can give inputs, or you can write the code of the inputs as well. Both are possible.
Okay. Okay. Like I can't drag and drop to get the block
It is
I need.
not that simple here. That's the issue. But one thing is there, like once you define that particular module, like you define DPWM module, okay. Then when you want to use it in voltage mode control, if you've already tested it, then you can just directly use it there. Okay, that is why when I told
Okay.
once you test a module, then you can use it.
Okay, sir. Okay.
So
The installing of Xilinx only taking my time.
yeah, it is actually a big software. Everything is there. Actually, I don't know why they're not giving proper support for Windows 11. They should make it simple, but I don't know why they've done that. Yeah.